I came across this problem that is a double integral in polar coordinates, and just setting up the problem is just a little bit more difficult, so I wanted to kind of make a support video on that. I hope you enjoy it. So here's the integral in question. It's a bit tricky, and I want to show you how to set this up. So the first thing is I'm looking at this x squared plus y squared right there, and when I look at that I immediately see r squared. So just the setup of this problem is making me think that we should switch to polar coordinates. So if we do that, let's have a look. Here I have a dy limit of integration, and then y is equal to this square root. So I do recognize this as the equation of a circle, but you may not. Let me show you how you could see that. So if one of the limits of integration is y is equal to the square root of 2x minus x squared, then this means y squared is equal to 2x minus x squared. What you could do is, this is the equation of a circle, and you could complete the square and turn this into an equation of circle and find the center and the radius. But since we've already identified this as a polar type integral, I'm just going to jump into switching to polar right now. So I'm going to use x equals r cos theta and y equals r sine theta, and just sub everything into this equation. So what am I going to get here? I'm going to get here r squared sine squared theta equals 2r cos theta minus r squared cos squared theta. Okay. All right, so now when you look at it, I think it's pretty clear. The sine squared plus cosine squared equals 1 in this. So let me just add r squared cosine theta to both sides. So r squared sine squared theta plus r squared cos squared theta is equal to 2r cos theta. And then sine squared plus cosine squared is 1. So r squared is equal to 2r cos theta. And then this means that either r is equal to 0 or r is equal to 2 cos theta. Hopefully you're familiar with this graph. R is equal to 2 cos theta. So let me take a minute just to draw this circle in a pretty way. So we figured out that r is equal to 2 cosine theta, and that gave us this kind of nice graph. So just to be clear, this is the point 2, 0. So this is a circle of radius 1 that has been shifted right 1 unit. But we're really not done here. There's still a lot of work to do. So first of all, when you look at these y limits of integration, the laser beam method tells us that we need to draw a line that is parallel to the y-axis. And then this laser beam enters the region at y equals 0. So there's the place that it enters, and it exits the region at this circle right here. So that means it exits the region right there. So we know we are only talking about this top half of the circle. Okay, so it's only the top half of the circle, but this rabbit hole goes a little bit deeper because it's not the entire top half of the circle. When we come here and look at these x limits of integration, this is going to tell us the portion of the x-axis that we're using, and this is the issue right here. This one is actually what makes this problem a lot harder. So that's right here, right in the middle of this circle. This circle is of radius 1. So right here is x equals 1. And according to this, if I drew a laser beam right here, then I'm going to start using the values of x that begin at x equals 1. So I'm only using these x's, and it's going out to x equals 2. So actually the region is just this portion of the circle right there. So that's going to make it a little bit harder when we set up our limits of integration. Okay, so I'm setting up these limits of integration, and this is where things get a little bit tricky. So when you set up integrals in polar, the first thing you do is you set up your r limits. So I'm just going to imagine a ray emanating out from the origin, and look and see where it enters and exits this region. Okay, so it's going to enter the region right here at that vertical line, x is equal to 1, and it's going to exit the region right there at the equation of a circle. Okay, so one of them's not so bad, right? I already figured out the equation of the circle here is 2 cos theta. But we need to convert this vertical line right there, x is equal to 1. I need to convert that into polar. Okay, it gets pretty ugly because x is r cosine theta. So the equation x equals 1 converts to r cos theta equals 1. You divide both sides by cosine theta, and that vertical line right there is r equals the secant of theta. So that's how they get secant theta as the place that it enters, and then the equation of the circle is the place that it exits. All right, now I've got to do the theta limits of integration. So the first part is actually not so bad. So if I look at this ray right there, then that's obviously where it starts opening, right? Oh, I guess, oh, whoa, it's mirrored. Okay, so I guess it starts opening like that. I'm looking at myself in the picture. Starts opening like that. So right there is theta equals 0. Okay, so it's actually pretty natural to get theta equals 0 as the place where it starts. But what about the place where it stops? Okay, so the last ray that we can draw that is still inside the picture is that ray right there, right? As soon as I go, I guess this way, as soon as I go beyond that, then now I start opening outside the region. So this point right here is where x is equal to 1. And also it's on the equation of that circle right there. And the equation of that circle is y is equal to the square root of 2x minus x squared. So if I want to figure out the xy coordinates of this point right here, I need to plug x into this equation. So hopefully you can see if you plug it in, it's going to be 2 times 1 minus 1 squared. So this is also y is equal to 1 there. Okay, all right, so that means this point right there at the top of the circle is x equals 1, y equals 1, and I just need to figure out the theta that corresponds to that. I think it's pretty obvious that the theta is going to be pi over 4, right? 45 degrees is right where that 1, 1 happens. It even looks like it in the picture. It's right there diagonal. But if you ever get stuck and you need to check it, you can just remember that the tangent of theta is equal to y over x. So in this case, that's 1 over 1. So this means theta is equal to the inverse tangent of 1. And that's where you can get that pi over 4 from. So this is going to go up to theta equals pi over 4. Okay, now what happened on the inside here? Right here, I have 1 over r squared squared. So that's where I got this r to the 4th right there. And then at the end, this was dy dx. So that's dA. And then people have been calling this the pirate formula, right? So there's r dr d theta. So you're going to end up with an expression that's something like 1 over r cubed, and you're going to have to plug in these cosines and these secants. So I worked out this integral, and I think that you guys are going to be able to do it. You have to know the antiderivatives of some trig functions, and really the only one that's kind of difficult is you are going to have to know the half angle formula. Let me just check and make sure I have it right. Okay, so I did do it right, and I think the only remaining tricky piece is that you're going to have to use that cosine squared is equal to 1 plus cos 2 theta. All right, so this is a tricky problem. I think, to be fair, this is probably one level more difficult than you would see on a like Calc 3 classroom level example, but that's okay. It's a good homework problem, so you got to practice harder than you play. So if you're still stuck working out the integrals, or if you have questions on this, let me know, and I can see if I can give you a little more support.